Alright guys, welcome to Planes Over It, and we are continuing with the radio navigation series that is being started. And the standard disclaimer, whatever images are there in this video are not owned by me. So let's just begin. Today we're going to do ADF and NDB. So ADF stands for Automatic Direction Finding, which is an onboard equipment loaded on the aircraft. NDB is a non-directional beacon, which is a ground-based transmitter and is generally in the low frequency and the medium frequency bands. What it does is transmits vertically polarized radio signals in all directions. Very important to note, vertically polarized radio signals. And how does it work is when the ADF that is there on board is tuned to the NDB's frequency that is being fixed, the transmitting frequency, the call sign is identified and the direction of the NDB is indicated on the RBI or the RMI that is on the aircraft. We shall not be discussing RBI and RMI in detail in this video because it is out of context, but that's the instrument that is used to show the bearing of the NDB. Okay, so principle of operation, the ADF measures the bearing of the NDB relative to the fore and aft axis of the aircraft. That's the longitudinal axis. So it measures the bearing relative to that. So when the loop aerial is placed in the plane of transmitted radio frequency, a voltage will be generated. I shall explain this in the coming few minutes. This voltage drops to zero when the loop is perpendicular to the wave, and when the loop continues again to rotate, it will induce in the opposite sense. So bottom line is the principle is relative bearing by switched cardioid. I shall explain all of this. How it works. So this is the wave that is being transmitted. This is the side view and this is the plan view from the top. So this is your loop. As you can see, this is your loop here. So the loop, whenever it is placed in the plane of the wave, there's maximum current when it is in the same direction. And the current keeps on reducing as it turns and it becomes zero when it is perpendicular to the wave, hence creates a null. Okay, so this null, again the point is, again when the loop is rotated, there's another null that gets created because of the other side. So this leads to a polar diagram of the loop as something like this, a figure of 8 with two nulls placed like this. Okay, now this doesn't give you a good position because it's two nulls and the direction of the beacon, though can be determined, is not pretty accurate. It gives an approximate direction. Now what to solve that, so problem, we introduce something like called a something called a sense aerial, or it's a simple dipole aerial which has a polar diagram like this. Okay, so these both polar diagrams are combined electronically as if the sense aerial was in the middle of the loop aerial. Okay, so this relative signal strengths get added up like this, and this is the polar diagram that you can see on the screen. Okay, that's how it looks like. Now this resultant polar diagram gives a cardioid. Okay, this is what is called a cardioid as a single null, as you can see here, single null. And this itself all alone would not be able to provide a accurate bearing. Now how do you improve the accuracy, because ICAO demands an accuracy of plus or minus 5 degree to the station. Okay, so what is done is the cardioid polar diagram is rotated, loop aerial is rotated clockwise, as you can see. So this produces a signal increase in signal strength of the cardioid, which gives you a right hand cardioid as well. So this improves the strength of this null and gives you a much accurate bearing. Okay, but now what the problem is, you cannot have a rotating aerial loop aerial on the loaded on the aircraft from the outside. So electromagnetic circuit is used to make the loop feel as if it's rotating by switching circuits, logic circuits, and hence this resultant polar diagram comes into play. Okay, and that's how the bearing is depicted onto the RMI or the RBI. Frequency and types of NDBs. Frequency is 190 to 1750 kilohertz, but most NDBs will be used between 250 to 450 kilohertz. Two types of NDBs. Locator and en route. Locator are low powered NDB co-located with the ILS approach to guide the aircraft onto the localizer. Range is about 10 to 25 miles. En route NDBs, they have a range of 50 nautical miles or more, and oceanic NDBs have ranges several hundreds of miles. That's because of the ocean effect. Okay, the range on the oceans are much greater, and they're used for homing, holding, en route, and airway navigation. Now, important point is NDBs for both the above purposes have become largely obsolete because now it is being completely replaced by the VORs. Even locator is barely there on most runways across the world. There's no more locator concept at all. And en route also has been moved by the VOR because it's much more accurate Doppler VOR and the ranges are further high. So we are discussing something that is kind of getting moving out of aviation. Okay. Now the emission is a 2 or 3 letter identifier. Okay, and the emission code is November 0 November Alpha 1 Alpha or November 0 November Alpha 2 Alpha. So these are the two types of NDB emissions that are there. So the problem is this is not easily detectable. Okay, so there's a device that is installed within the equipment in the receiver, ADF receiver on board the aircraft. It's called a BFO, beat frequency oscillator, which offsets the received frequency within the receiver to make it detectable and audible. Now, for Alpha 1 Alpha, you require BFO to be on for manual tuning and also for identification and monitoring. Alpha 2 Alpha, you require BFO to be on for manual tuning, but identification and monitoring it is not required. Why? Because the Alpha 1 Alpha part is the emission of an interrupted unmodulated carrier wave, which requires the BFO to be on for identification and oral reception. But the alpha to alpha is emission of an amplitude modulated signal. So this is unmodulated carrier wave, interrupted unmodulated carrier wave, which cannot be heard. But alpha to alpha is emission of an amplitude modulated signal, which can be heard on a normal receiver. So hence, identification monitoring BFO should be is not required. It's off. Okay. Factors affecting accuracy. Okay, that's important for us to know. So designated operational coverage. This is called as DOC. So DOC of NDBs is during the daytime protection ratio, which is signal to noise ratio, and what happens is what you want signals you want and what are unwanted. So that improves your accuracy. So according to the NDB's performance, it is good to use it in daytime. Nighttime, it's not good. Static interference is pretty simple. That is precipitation, thunderstorms, or any electrical activity that is there in the atmosphere will disturb the frequencies, because it collides with the water droplets or static electricity discharge, which affect the LF and MF frequency. Okay, so that will make the needle move rapidly and will absolutely not give you any bearing at all. Night effect is something to do with what we discussed in the earlier video. At night, what happens is the D region that is there disappears. So this allows the skywave contamination to take place. So skywave contamination happens, and the surface waves gets contaminated because of the skywave. So this will reduce your the range accuracy of the bearing, and it becomes very significant from 70 to 100 nautical miles from the NDB, where you are actually the needle will just try to hunt for the NDB. So to avoid all of this, you should avoid to avoid the night effect. Fly in the day is simple, and avoid using ADF within 1 hour of sunrise and sunset. And you can always cross check with other navaids or any other charts. Station interference is near the antenna, that is the NDB. You have any metallic installations or any other disturbances that cause the frequency to be troubled, interfered with. Mountain effect is something to do with reflections and diffractions due to terrain. So this is very common in the valleys if you're flying low, and of course can be avoided if you fly high up above the mountainous area. So basically in the valley, or ADF accuracy is degraded largely. Coastal refraction. Now radio waves, what happens is they speed up over water due to reduction in absorption of energy by water. The terrain absorbs more, water absorbs less. So there's more attenuation on the land. So what happens is this speeding up of wave causes a diffraction turn of the radio wave, refraction and diffraction. So this pulls it towards the coast and gives the wrong bearing. But this can be avoided by using the NDBs which are closer to the coast, which because that will not give any refraction chance because you're right at the coast, the NDB, or you can fly higher because that will minimize, and use signals that cross the coast at or near 90 degrees, because 90 degrees you will have no refraction, it'll go straight through quad, because there's no bending of the radio waves basically. Quadrantal error is because of the bearings basically. So on relative bearings of 045, 135, 225 and 315, there's a airframe quadrantal error. Okay, so the polar diagram gets affected because of the strong electrical field that is aligned with the fore and aft. So whenever you are in this relative bearing of 45 degrees, 135, 225 and 315 in each quadrant, the error is maximum. Okay, so the only way is the manufacturer has to test this and load it in the equipment to remove this error. Angle of bank is pretty simple, since the if you remember what I told you was the NDB transmits in vertically polarized waves. So the moment you bank, the vertical polarized wave hit at a different angle to the loop, causing it to give reduce the accuracy. And ADF NDB has a lack of failure warning system, so the accuracy you do not know at all what's the if the instrument has failed, or what is it showing. So that is one factor that affects accuracy. And bottom line is the accuracy which is required by cow, the minimum is plus or minus 5 degrees within the designated operational coverage, which is during day only. All right. Factors affecting range of ADF NDB. Transmission power, which the range is directly proportional to the square root of the power. So if you have to double the NDB range, you have to quadruple the power of the power output of the transmitter. Range over water is greater, this is how it gets affected. So 3 times this is over water, 2 times is over land, because of the attenuation capacity of the land is more. Then lower frequency, because ADF uses lower frequency, greater surface wave, lower attenuation. Okay, so this is uh, what affects the range. So if it's lower frequency, greater surface wave and lower attenuation, it travels faster, farther. Precipitation reduces range, of course, as we discussed. It decreases accuracy also, and it also reduces the range. Alpha 1 alpha NDBs have greater range, and receivers quality of also affects the range. All right. Now alpha 1 alpha NDBs have a greater range because of the fact that they are unmodulated carrier wave in, you know so that is why the range is better. So then again you need a BFO to keep it on for both even manual tuning and also for identification and monitoring. And the receiver quality is of course what depends from company to company what quality it is. So I hope you guys understood the basics of the NDB and ADF. If you guys have any doubts, please drop a comment below. I will surely get back to your doubts. And thank you for watching, guys. Subscribe to the YouTube channel if you like this video. Give it a thumbs up and like the Facebook page for also regular updates. And share it with your friends too. I'm available on the links shown on the screen. I'll be attaching a quiz on this video in the description. Find the link below. Cheers and happy landings, guys. Have a great day ahead.